Right, everyone. Welcome to day 3 of the Hypermatrix workshop. I'm very happy to be here with Richard, Liubov, and Mano as well here in the room, some people online. So it's been a pleasure to have these 3 days of talks. It's, as I was mentioning to Richard earlier, it's been really exciting to be here in person, to be sort of on location and be discussing these things with a blackboard behind me and everything. So this final day is about hypermatrices proper. So we had a day 1 that was more focused on NRLE algebras. We had a second day that was more focused on hypergraphs and in different ways and rewriting to some extent. And this final day is going to be myself and Josh Groshaw, my collaborator, that we're going to present to you some results or some hints at results about some of the products that with hypermatrices. So before that, I'll begin with my talk, introducing some of the basic ideas and what we call hypermatrices and what these objects are for us. And it's going to make a lot of contact with Richard's presentation in particular and Victor's as well. My question is, what is NRE associativity? This is the motivating question that I've been thinking about for the last 2 or 3 years. I guess I've been saying 2 or 3 years for a while, so maybe it's a bit longer, but it's essentially that. I haven't had the time until very recently to make proper efforts into it because I was transitioning from a career in differential geometry and theoretical physics. So these topics, although they are closely related, they were not following up any of the previous lines of research. So I stumbled upon this question about, about ternary algebras. So a common friend here, Jose Adolfo Azcárraga, introduced me to my mentor during my undergrad, introduced me to this idea of Lie algebras. So the story is that I was thinking about Lie algebroids, which are a certain kind of generalization of Lie algebras. And so my supervisor at the time pointed me to this paper by Azcárraga, who's a close friend of mine, but I never knew that he wrote this review in 2010 about NRLE algebras. And there I found that you can generalize Lie algebras also in the number of arguments. So the simplest generalization from a conventional Lie algebra is what we call a 3 Lie algebra, or ternary Lie algebra, sometimes also called a Filipov algebra, that satisfies these properties. So you have a fully symmetric, fully antisymmetric bracket. The antisymmetry of the bracket is not so important to me. You might want to think of just 3 Leibniz algebras where you don't assume any antisymmetry of the bracket. But the important one is the Jacobi identity. It's the identity that is written here, which is, it might look messy the first time you glance at it, but it's actually very easy to read. You just need to think about the xy dash operator, which is a linear map, obviously. You just need one argument plugged in the 3rd position. And you can observe that the property is basically that xy bracket has a derivation behavior, right? So when xy acts on ABC, the product ABC, all it does is it hits A first, plus hits B, plus hits C, right? So it's a very simple formula, although it looks messy at first glance. So
a single element is not a derivation, but 2 elements
exactly
define derivation.
Correct.
Yeah.
That's precisely the.
What about if you interchange y, x?
So in the case of Lie, then you get minus the same element.
Yeah. Here.
And in the case of Leibniz, you get exactly the same behavior, but it's a different map.
Yeah,
because it's for all. Yes. It's the same form. Yes. So actually, in the paper by Azcárraga from 2010, I think it's called a review on N Lie algebras or something like that. But you go Azcárraga review Lie algebras, you will find it. There is a detailed account of this particular event. So, in fact, you can find that these derivations form themselves a Lie algebra or a Leibniz algebra and so on. So, the question that really bugged me, so there's a fair amount of literature on these guys. By the way, there's a very simple example of, actually, let me see my own camera, just in case I want to frame myself. Just put a small. Well, actually, it's not going to be very useful, so I'll intuitively. I'll just write a small example on the blackboard. So if people are wondering what is that, the hell is that? N algebra. maybe you remember from high school that you can define the cross product of two vectors as this kind of determinant formula. Right? So you write x1, x2, 3, y1, y2, y3. Right? And we all know that this is Lie algebra. This is SO3, right? Is the infinitesimal component of rotation. Yeah, so symmetries in three-dimensional Euclidean space. Now, if you can see that this formula, the idea of having one line of vectors and the other lines of components of vectors can generalize to any dimension, right? As long as it's a square, you can compute the determinant. So what about if we reduce the dimension? Well, if you reduce the dimension, the formula will look like something like this, right? Oh, sorry, there's two. And then I have only one line to fill, so I'll just write A1 and 2 maybe. And this looks exactly like what you would want to think as a sorry, not this, but when A is a complex number, right? So this is the complex structure in C, where you see C as basically the two-dimensional vector space, right? So, okay, now what happens when I take it to the fourth dimension, right? So I define a ternary product where I just write the same determinant, and I write E1, E2, E3, E4, basic vectors. And I have X, Y, Z. These are vectors that you want. We can call them whatever. And then you do the same. X2, X3, X4, Y1, Y2, Y3, Y4, Z1, Z2, Z3, Z4. So this is the formula that you compute. And when you multiply everything out, you will find terms that contain some X, some Y, some Z, and some E. Right? So you'll have just a cubic components on E1, E2, E3, E4. So this thing satisfies exactly that property. If you just compute this long formula, you just check that it satisfies this Jacobi identity. So ternary algebras, and of course you can keep doing this for any dimensions. The higher the dimension, the bigger the determinant you have to write. They all satisfy the corresponding n-1 array Jacobi formula, which, as you can imagine, is easily extended. You have more arguments. It means that you have to fill all arguments but one, and that argument will behave like a derivation.
So this is Euclidean.
Yes. Yes.
How about in Gaussian space?
So you can actually
in Gaussian space you have a natural 4 form, epsilon 0, 1, 2, 3, and you can feed in, but it's more complicated.
You just need to account for minus signs. You just need to account for minus signs.
Yeah. It gives you some properties with light.
Yes.
Light vectors and space vectors.
Yes. So in fact, in this reference by Azcarra, you will see the general construction. It constructs it for a general metric, regardless of signature, of any signature. But this construction is very natural. When you think about what this is doing, what this is doing is basically saying, if you give me an n-dimensional metric space, anytime that I define a hyperplane, you will be able to define one orthogonal remaining direction. Yeah. So if you give me enough arguments with an ordering, I have only a unique, well-ordered direction, right? Yeah. And that's the result of the product. So that construction is the canonical example of an n-array algebra, because in n dimensions you get an n-1 dimensional structure, right? So in dimension 2 we call it a complex structure. In dimension 3 we call it the cross product. In dimension 4 we don't call it anything. And dimension 5 we don't call it anything. But they are these kinds of guys, right? So what piqued my curiosity is that, as I mentioned, for example, the cross product is the infinitesimal component of the group of rotations in 3D, and this is a group. So it's a very well understood algebraic object, right? It has some axioms, and we understand it has a property, and all good. So this is what we call the Lie factor. It has a fancy name, but it's a simple idea that given any Lie algebra, you can find a unique, simply connected Lie group that integrates it, meaning that its infinitesimal component becomes isomorphic to the Lie algebra, right? So given any two Lie algebra, so traditional Lie algebra, I can find a group that will integrate it. So in a particular example of the cross product, this process will give you the rotations.
Yeah, you can find only simply connected.
Simply connected. Exactly.
The group itself is...
The group is not unique.
yeah, it's usually...
Other components or other covers. Yes. Exactly. So, but the point is that there is such an object that if you define properly, in this case, Lie group, so it's a topological group with the smoothness of the operation, that when you look at the identity infinitesimally, you recover the structure of a Lie algebra.
It's exponential.
Exactly. So you go exponential in this direction, or you go infinitesimal in this direction. So the big question is, if I give you a 3 Lie algebra instead of a 2 Lie algebra, what should I put in here? Right? What is the infinitesimal analog of the exponential of a 3 Lie algebra? So this is an open problem. Nobody knows. It's unknown where you put there. And so I began looking at what I called cubic matrix algebra. So the hypermatrices that we are looking at today, simply to see if I could find some examples of this kind of operations. So I was looking at these products in particular. I'll show you more later. Which they came from Richard's paper originally, and but also they were sort of naturally defined simply by looking at some combinatorics of indices. So I'm not going to focus too much on that right now. All I wanted to point out is that in this paper from you and from Victor and Olga and Shitov, there was found that when you scan this product, I think it was in this particular one, I think it was the middle one, if I remember correctly, they were trying to see if for either of these two, there was some axiom, some property that was satisfied. And only this formula was found, and this was mentioned on Monday. This is called a semi-heap, right? And it has this particular property. So what was very interesting is that by looking at the literature, by doing some search myself, some preliminary search, we found out that there was no other known forms of associativity, generalized associativity, right? Obviously here, the idea is that a group here, which is the exponential of a Lie algebra, has an associative operation. An associative just means that you can group the bracket in whichever way you want. So we were thinking 3 Lie algebras that have this Jacobi identity that look like that might be coming from something that have some kind of ternary associativity, whatever that means in the particular case. And so we looked at the literature, we found that really there wasn't that many options because there was only this. And if you try to make this into a 3 Lie algebra, you can't. It doesn't work in the usual way of building a commutator of one of these. It just doesn't work. So it was very surprising to me that there were no other forms of associativity that were known. So I got curious. And so in order to understand these products, I developed a diagrammatic language just to account for how the indices are being contracted, because I felt like, when looking at these formulas, I was getting a little bit disoriented to see where the indices go. So I just started to draw pictures just to make things a little bit clearer. Yes, and so I actually took inspiration from graph theory, what people do in graph theory, where in graphs you have a adjacency matrix, and this is what we were talking about on Monday, where you have the indices, sort of some intermediary index P, and then 2 indices I, J, so you represent the adjacency matrix by this kind of pattern. And the observation here, what made pictures more interesting than just good guidance, made them mathematically interesting, is that when you study why matrix multiplication is associative, you can directly connect that fact to the fact that there's path transitivity, meaning that if you can connect I to P and P to J, that means that you can connect I to J. Right? So this observation, which is absolutely pedestrian, there's nothing deep about this observation, to me was really key to try to develop a research program around these products. Okay, so how does this work? It's very elementary, but the basic idea is the following. So if you have a product that looks like the thing at the top, and I'm using some colors just to highlight what indices are being contracted. Big disclaimer, the order of the indices are somehow ambiguous. So you can think that all these are undirected edges or completely symmetric matrices, if you want. We will see that the problem of the order of indices is crucial to get the behavior that you want, but for now, just for the diagrams, just think that they are all fully symmetric, just for the sake of diagram. So I looked at that that definition, and I thought, well, clearly each object I, J, K has a triangle between three vertices, because that's what I have. In the direct generalization that a matrix is a single edge of a graph. So in this sense, a single edge here, a hyperedge, is a hypermatrix. And then all I do is I fill in the colors of the indices that are summed up. Okay, so that has the shape of a fish. That's why we call it a fish. And you heard in Victor's talk that's how people start to refer to this product now, which is a good thing. This is the other pattern. This was the product in Richard's paper that has this particular contraction pattern. So you see that P with P in the first and second, Q with Q in the first and third, and R in the second and third arguments. So that's the pattern, and we call it three-fourths in case there are any Legend of Zelda fans in the audience. It resembles like that symbol in the video game, so we just call it the three-fourths. And then the one that perhaps grants the most attention, at least today in today's session, is the so-called Zapata-Carratala. So Zapata-Carratala wrote a paper in 1990 where they identified a ternary associative scheme, as they called it, which is essentially a ternary relation in a set. And it was defined, or rather, it was it's not a ternary relation, but it's an operation on ternary relations on a set, and it was defined precisely by this formula. You would have to replace times and sum by and or to get it into a more conventional relation form, but that's essentially it. So this particular pattern is curious because you have a triple index contraction, and you have the standard indices just standing along each other. Okay, so this was the observations that I was doing, and since I joined the Wolfram Institute and I started work there about a year ago, we've been trying to develop a code for this. So can I? Oh, it's here. So I'll try to show you that we have implemented Plex diagrams in Mathematica. So you can actually just draw a picture and define a product, which is pretty cool. Actually, I need to run. Hopefully this will not explode this time. That's good, because yes, but thanks for the reminder, because I was going to talk over it. But yeah, it's good that I'm just setting the scene. Okay, already. So I'm going to share the screen instead of the window. Give me a second. Where the hell is Zoom? Interesting. Oh, hey, Victor. Didn't see you before. So let me just share the screen. Oh, screen, yes. So actually, let me meet this. This should be fine. Okay, so we have coded arrays. Arrays are the structure that we're looking at. So it's very important that we distinguish. Oh, there are some comments here. So it's very important that we distinguish what is a tensor and what is an array. So an array, for me, is just a list of numbers. There's no structure, no linearity, assume nothing, just numbers in a table. And so the code that we have deals with arrays. It doesn't assume any linear structure, so you can do a lot of things that are not well defined in linear algebra. So they are some kind of artifacts if you have a linear algebraic mindset. But just bear with us because I think there's a lot of interesting algebraic structures there.
Always square or?
In this case, for simplicity, we're going to look at just cubic, so square, always what we call regular, right? So regular, it has n by n by n by n. Yes. But of course, many of these need not be regular, because if you look at these diagrams, all you require is that the indices that are incident, right? So where each triangle is incident, that dimension is the same. But they can all be different among each other. So you need that the third index and the second index and the first index are the same. Yeah. So for algebraic purposes, we keep things cubic, and not only because of simplicity, but also because otherwise you would not have closed operations. Yeah. Just like in matrices.
Also because here at least you can switch the tensors.
Yes. 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 Exactly. So okay. So. This code just generates so let me, just in case I want to run something live, run everything. So this code just generates arrays. So you can see that it's generating, for example, a symbolic 3x3 array. So it's more like a traditional matrix. But we can also generate 2x2x2 arrays over Boolean values, for example, some complex values. We can have this. So I like to show, by the way, I like to call these things the n by n by n arrays. I like to call them cubices, or like a cubics, like a matrix, like cubics. And, we have a little funny representation of the thing as a little cube. This can be bigger, of course, can be, higher dimensional, and it's a bit bigger. Or have other representations or whatever. And the point is that these kinds of products, the ones that I just showed, have this kind of shape. They take three cubes and they give you another cube. Just like two matrices multiplied together to give you another matrix. That's just a visual representation of that. So what are those products? So this is what I call contraction operations. And so a contraction operation is a generalization of the dot product or the matrix multiplication product. It's nothing more than that. So you can see here that what I call the operation index contract here basically tells you that you take two indices, and then you specify which ones are contracted, and then you specify which ones are kept at the end. So you can see that this in Mathematica language means Hadamard product, basically, so a component-wise product. So index contract, when you don't contract, is just Hadamard product. Index contract, when you do contract, so for example, this is A, B are matrices here, are n by n matrices, 3x3, I think. So when you do I, J, J, K, but J is missing from the output, right? Then it means that J has been contracted out. So this equals A dot B, which is Mathematica code for matrix multiplication, right? Okay, so then we define the ternary products. So these are the products. So the Bhattacharya-Messner is here. You can see that the pattern is IJP, IPK, PJK, which is the same as before. And the output is always, you can see in here, the output is always IJK, 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 IJK. So all these patterns before it, you don't need to get lost in those terms. It's just different combinatorics. And the only constraint is up to orderings, you need to have as many contractions as necessary. So as you were saying on Monday, if you have 9 indices, you'd have to contract somehow 6 of them. But it can be done in many different ways. So, for example, the first one, what it does, it contracts 1 from each input, but 3 times. But the other 2 indices are just not summed over. So you have I and I are repeated in here from the first and second arguments, but they are not summed over. So that is allowed. But for example, in the 3/4, which is the one that Richard used, we have I only in one argument, J only in one argument, and K only in one argument. So these are possibilities. So up to reorderings of these indices, which there can be a few, these are the 5 possible well-defined operations. Okay, so what's interesting about this? Well, there are some properties that they satisfy. So for example, the 3/4, so the identity cubics, let me show you what the identity looks like. So the identity cubics looks exactly as you would imagine. It's what we call an identity array. So the identity array for the 3x3 case is just the identity matrix. The identity cubics will look like this, right? So it will have this form. And so if I take this and I say, I think it's 3D. How do I didn't run this, sorry. So you would see that the analog of this is cubic 3D of this. It looks like that. So it's a cube, and if you look closely, I mean, it's a bit weird, but if you look closely, oh, it's not quite right. Oh no, this is a partial identity. Sorry, this is not the full identity. So this is the identity. Let me just identity array. Okay. So if I change this for identity array, and you just specify that you want it to be Boolean, for example, you want it to be 3 by 3 by 3. So that's the identity array. So you can see that there's all zeros except for one in a corner, one in the middle, and one in another corner, right? So that's what we're calling ID. I don't know if I defined it over here, but that's what we're calling ID. It's here. So if I run this thing, ID is that is the analog, the ternary analog of the identity matrix. So for example, it has some identity-like properties. So if you take it into Richard's product, what I'm calling the tree-force here, it behaves like identity equals identity. Yeah. Just like in matrix multiplication, identity and identity is identity. So it has some similar property. So that's also true with the Zapata-Carratala product, which is this other diagram. But for example, you stop seeing more natural axioms. Like for example, if you do element with identity, you might expect that you get the element back, but that's not the case. At least not for all the possible reorderings. So we have this little code here that checks for all the possible equations that are true with these identities. And so we find some of them. I mean, we find all of them, and some of them, some of the combinations, I mean, are true identities. So in any case, the point here is that arrays have a richer algebra of identities, because it's not only the ternary identity, but also what we call the partial identities, which, as you can imagine, are, if you imagine the identity matrix, you can think of it as being projected in or extended in the vertical direction, in the horizontal direction, or in the lateral direction. And each of them has an identity-like behavior. We call them red, green, and blue because there's 3 of them, and we call them partial identities. So they actually behave in this kind of way. So for example, if I do red, 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 I get red back. But also if I do arbitrary element times green times blue, I get the element back. So there is some subalgebra of those products.
Almost like Rubik's Cube.
Yes, there is some, and that big list over there. That's particularly for the Zapata-Carratala. I could run it for the tree-force as well. So if I do ID search, ID equation search for a tree-force, which is your product, Richard, you see, we get some equations. Yeah. We get fewer, but still some equations. And if the equation contains a 5, like these final ones, or even these ones over here, it means that the equation has this. So 1, 2, 3 are red, blue, green, which are these identities. 4 is the ternary identity, which has the diagonal ones, and 5 is a symbolic generic array. So these equations, for example, this one here should be read as red times arbitrary array times cubic identity equals arbitrary array. So it is a identity-like behavior where those two elements are behaving like a neutral element. So for your product, we have all these equations, which is many of them, right? So all these equations are the ternary analog of when you write down matrix times identity equals identity times matrix equals matrix.
Yeah.
So those simple two equations become now how many?
Yeah.
Whatever, 4 times and whatever. It's a long list of identities that we get in is the price we pay for being ternary, right? So it becomes much more rich. Okay, so this is about identities. Now, the interesting question that I had in the beginning: what is associativity here? So, Richard, this is the code that we wrote to check for computationally check for. So this works for arbitrary products. Any product you want to define, you can put it, and it works for arbitrary expressions. So the way it works is we generate. So the arguments look like this. You say find ternary clone equations. You specify the number of products that you want to consider, like the fish or your product or whatever, and you can specify more than one, and they will do all the possible nestings of the products, and then you specify the number of elements that are going to be included. So, for example, this first argument here is going to find in the fish product how many equations exist of the form A, B, C equals one of the 3 elements A, B, C, right? Or equal one of the permutations of the elements. And of course, we all know that the fish doesn't have any symmetries, so the output of that first line is empty.
So I have a question.
Yeah.
But you probably want some very specific equations still, like you don't want to check for any of combinations resulted in anything. You are very specifically probably want to find something very, very interesting, very beautiful. We want to basically brute force with all of them.
I mean, but we don't know what we want to find, so we need to find anything.
Find it.
Well, you search for everything. You search for everything.
Yeah, but what do you, like, where you can get your intuition what you want to find? So
I was trying to do this by hand and by intuition, and because it was helpless, there's no intuition. You just brute force all possible cases. And if you find some, then you're trying to think, where, how do I understand this? But first you need to know that some exist, because it's not guaranteed that some are going to exist, right? So,
yes.
So
what I was asking was more whether you had also a process of filtering out these things.
No, before we need to know, I mean, I don't know, because before we need to know some, we don't know any.
I understand.
So after you find some, then sure. Once you see some and they look too complex or too simple, then you might want to do something else. But the first step is to know if there are any at all, because we don't know if there are any. Like, that assumes that some exist, and if some exist, then you can do something else. But if the output is the empty set, then there's nothing else to do,
sure.
Right? So anyway, so it's I really want to everyone to understand that what this is doing is really checking the clones. I don't know if people are familiar with clones. Clones mean that you basically create all the possible nestings of products. So what this is doing in the first instance is doing fish of ABC, then fish of ACB, then all permutations, and then it computes. So by the way, all the elements are numerical. We generate some small sparse random arrays, and then we check all the products numerically. If we get a positive check for an equation of the form fish ABC equals fish ACB, for example. If we get a check, that's numerical, it's just some numbers being checked. Then we write that symbolically, and then we do a symbolic algebraic computer algebra check, right? And so, of course, as you know, Victor here in the Zoom call and Richard know, many of you, I'm sure, know, the fish doesn't have any symmetries. Therefore,
because it's broken.
Exactly. So, reality check. When we try to find some equations that only involve A, B, and C, we find none. However, when we try to find equations that involve A, B, C, D, E, 5 elements, we should be able to find the axioms that you found in the 2009 paper. And sure enough, we do, right? We find that an expression that looks like this, so fish of fish A, B, C, D, E, is equal, just not to use equals because that's reserved in Mathematica, but it's equal to fish A, then D and B swapped in here, right? And E. So, of course, and then we find all the other equalities, the 6 other equalities. So these 6 equalities are the formula that we had before for semi-heaps. So that's good. So it means that the thing finds what we know exists. So when we run this for example, the Zapata-Carratala product, this takes some time. for this laptop, it takes about a day to run all the possibilities for 5, and it finds nothing. So we know for sure that product has no axioms that only involve 5 elements. Yeah, go on.
No, go on.
Yeah, but could you check maybe next time with Wolfram? No.
Yeah, with the 40
With 40, yeah.
Yes.
So this is
But that would be C3 grade.
yeah. So that will be later, because this is primitively the product itself without any. So this is not even considering the vector space structure.
Yeah.
It's only the algebra.
No grading, no.
No, so this is only the pure operation in some sense, because these are sort of pure axioms. Not for example, we're not considering linear combinations.
Yeah.
So in this search, to say that this term equals this term is not equivalent to saying that that term minus that term equals 0.
Yeah.
Because in this search, it is really
There's no-
term equalities, right?
no
We're
linear structure.
exactly no linear structure, which it's exactly what we want, because the idea was to find the notion of n-ary associativity, not n-ary linearity, which we already understand, right? And so it is very shocking that, at least to me, that when we run, I mean, you can see this is empty. All the other products. I mean, this is again fish table is just another. It's just a fish. So you can see that for all the other products, Balthasar Messner 3/4, which is the one that you have in your papers, boat, blades, empty. We have no axioms for them. I can tell you that I should have put it here, but I run the same algorithm for 7 elements, where you'd have 3 nested brackets instead of 2, still empty. Nothing comes out. We don't know for 9 because it was too long and we couldn't check.
What do you mean? What do you mean too long? Then it's
Too long that we didn't finish the search
No, 7 makes sense because it's
for about a week.
third iteration.
Yeah, so this is three nested.
From 3 to 5 is first iteration.
Yeah,
And from 5 to 7 is second.
iteration. Yes.
The next iteration, I would say.
I had hopes for the 9th iteration, but it's just too long. We didn't finish the search. It
okay.
was just
And some
no.
computation. Yeah, I understand.
Yeah.
But computationally, you couldn't parallelize the cluster, whatever it is.
We could. I mean, this is not rocket science. It's just multiplying arrays.
Yeah, exactly.
But I mean, we could do it if we really. But this is a. I mean, this is a
Common sense.
The
Yes.
number of conditions is growing faster than the number of variables.
Yes,
Of course.
just because right now we train models which are really like larger.
Yeah.
Ones.
Yeah. I mean, the point is this is only an experiment. We don't. I mean, because otherwise, I mean, this has no end. Like you don't know when to stop. The fact that there's already that this tells you that these algebras have no 5-element term equations. This is already very shocking to me.
Yeah.
I mean, or shocking or mysterious, because it basically tells you that whenever you're doing array algebra, except for the case when you're doing fish, which, by the way, I think I explained on Monday that the reason why, I mean, the way I understand that there is an axiom in here is because you can actually collapse the product into a matrix product. Because you can group indices in a multi-index of 2 and a multi-index of 1, and then you can see the fish product as just A times B transpose times C, right? And because you can do that, and it's associative, and the transpose is strongly compatible with the associative product, then you get an axiom. But in any other situation, which are products that you cannot write as a matrix, as a recombination of matrix multiplication, there seems that nothing happens. It seems that when you ask these products, what axiom or what behavior do you have? The answer is nothing. So to me, this was really mysterious, and so this is kind of the punchline of the talk, in a sense that we have the machinery to do these searches and to, if there is anything at all, we will find it. But there might be, as you will see in Josh's talk after me, that there could be an argument for why these products have no term identities whatsoever. This is a proof in progress. So the other thing I wanted to show you is that so it's the Plex diagrams. This is where I left it in my presentation. So so far this is just a matrix algebra in some sense. So, interesting. This was, it's some error. So Plex diagrams are exactly so this is the mathematical language implementation of the diagrams that I was showing you earlier. So all you have to say is draw a diagram for this number of indices, right? So I have an index 1, I have an index 2, I have an index 3, and then you just group them in terms of the matrices or the hypermatrices that will contain those vertices. So obviously, this diagram represents conventional matrix multiplication, because you say I have a matrix with indices 1 and 2, I have a matrix with indices 2 and 3, and then you specify that you contract index 2. Mm-hmm. So that's matrix multiplication. So this is the graphic representation of that, which you can see index 1, black, it's a free index, index 3, black, it's a free index, and then anything gray in the middle is going to all collapse and form a single edge at the end. So similar with here, these are two hypermatrices, two ternary hypermatrices, and then you are contracting indices 2 and 3. So the first hypermatrix has 1, 2, 3 indices, the other has 2, 3, 4 indices, and they are contracted at 2 and contracted at 3. So the hypergraph that you draw is precisely this. And this hashtag 1, hashtag 2 is basically represent the order of arguments. So you can, and similarly with Zapata-Carratala, and similarly with blades and so on. So the idea is that there is this function that says Plex to product, which allows you to draw the diagram or specify the indices. And now this is actually something that can operate on elements. So when I write Plex to product of this diagram AB and I compare it to the mathematical code of A.B, it says true. So it means that just by specifying this diagram, I can actually operate on elements. So it's a nice user interface to you can draw whatever product you think is interesting, and then you have something ready to compute on the appropriate size matrices. So here's the few products that I mentioned before. So I have the Zapata-Carratala, I have the blades, which is kind of a Zapata-Carratala-like, because each of these 4 and 5 are contracted like the 4 in Zapata-Carratala, because they are triple contractions.
You have to go to 3 dimensions.
Yes, they don't fit in the plane.
Yeah.
And you have the 3/4. This is Richard's product. Mm-hmm. We have the fish, and we have the boat, which is a kind of an ugly product in some sense, because you have you can contract here or here, you can contract here or here. The point is that you have 3 indices left, so it's so. The punchline of all this is that, except for the fish, which we know is a bit special because it can be written as matrix multiplication, for the others that cannot be written as matrix multiplication, we know no term identities whatsoever. And that's the big question. So my approach, I have 2 candidate approaches to deal with this situation. The first one, the first line of attack is to basically naively say, okay, so I'm going to do model theory, basically. I'm going to take the smallest cases of my algebras. I'm going to take 2 by 2 by 2 Boolean hypermatrices, and I'm going to just compute the multiplication tables of these algebras, or what I like to call them cubles, because they're really not tables. They are tables of 3 arguments, so they are kind of cubic tables, so I call them cubles, whatever. So I compute the multiplication cubles, and then for example, we define in this case, we define the Boolean, the cubic set. What I call the cubic set is all the Boolean valued 2 by 2 by 2 arrays. So there are 256 such elements, which is just 8 elements, can be 0 or 1, so 256. And then what you do is you take any 3 of those 256 and you multiply them with each of the products, and you just compute. The result is going to be one of those 256, and so you just write down computationally, just memory, you just store all the multiplication table. And so I'm in the process of doing this because it is very computationally expensive, apparently. I mean, when you try to do this, it's just arithmetic, but it takes a long time. It's easily parallelizable, trivially parallelizable. So it's very easy to make very efficient, but I just don't know how. So we can do this. But the point is not so much that it's difficult. The point is, once we have these things, for each dimension, so 2 by 2 by 2, 3 by 3 by 3, 4 by 4 by 4, for each of these dimensions, there's a single multiplication cuble pair product, right? The fish defines a cuble. The Zapata-Carratala defines a cuble. The 3/4 Richards product satisfies a cuble, right? And so the question is, how can you maybe tell them apart? If you just have the cuble, which is this big, 256 by 256 by 256 table of zeros and ones, how can you tell them apart? How can you, And so that's one approach. If anyone has any suggestions or any ideas on how to compare 256 cubed tables, I'm willing to listen. What is a good strategy there? Because that's the smallest one, because then you will have to do it for 3 by 3 by 3, which is much bigger, and so on. So that's one approach. That's the kind of numerical raw approach, where you just compute everything, and then once you have the final specimen of the computation, then you try to analyze it. The other approach is the kind of the complement of that, and then I go back to my presentation, which is, if you're looking for axioms of associativity, of NR associativity, you might wonder, how do you implement these axioms in the first place? So this is where I have the idea of what I call diagrammatic simplicity, which is sort of taking the complement of what I was saying before, which is literally computing every single case one by one. This is taking the most abstract sort of approach to what happens in matrix multiplication. So you can abstract matrix multiplication to be essentially this pattern, which a lot of people would recognize as morphism composition in a category, or the transitive closure of relations, or etc. So the way that you can extract the associativity axiom out of this kind of construction is if you label each of your edges FGH, and you apply that rule, but you keep the name of the label as consistent from the history of the rewrite. Right? So if I apply the rule on the left, I will call this new edge FG because it comes from FG. And if I apply it on the right, I will call it GH because it comes from GH. And so the idea is that then apply the rule again, I get two edges between the same vertices, right? These vertices could be labeled 1, 2, 3, 4, right? So the names the IDs are kept. And so I get two edges between the same vertices. So one is called FGH, the other is called FG bracket H, the other is F bracket GH. So the statement of associativity is that indeed this should be a fully confluent system. So there's no ambiguity of how you express the final. So with that idea, you can actually extend. So this is what people call a semi-category, because it's just associativity. If you also want the unit property, that F composed with unit is F, or unit composed with F is F, you get that property. You can do it simply by writing that arrow F, then you add this rule, which whenever you find a vertex, you add an edge. And then you compose using the first rule, and then you now get two edges on the same pair of vertices again. And so by the same principle, you force these two to be equal. And that's exactly the equation of unit. So it's a principle that is very elegant. It works for a lot. So for example, dagger means reversing the order. So you have F, you reverse it, you get F dagger on the other direction, but you can reverse it again. And you get F dagger in the direction back, but you get the original F and F dagger both going in the same direction. So again, the same situation. Two vertices, two edges, different names. The names should be the same. So you get the property of idempotency of involutions, right, of daggers. Similarly, if you combine daggers with composition, you can get the anti-homomorphism axiom, which is this idea that transpose or dagger permutes the order by this simple diagram. You have FG. On the one hand, you can compose first and get simply FG composed, or you can take daggers first. In fact, there are two steps there to just summarize it. And then you can here compose, or you can here take dagger. But in any case, you get a final state that is between the same vertices. One is called G dagger, F dagger, the other is called FG dagger. Same principle applies, you make the names the same, you get that. So you can go on and you find a lot of things. You find operats, which are a bit more sophisticated categorical objects. Of course, you find semi-heaps, which is the big, quote unquote, big discovery that we made. This is our main contribution to the field. The only result that I can claim to Richard that we did something, which is discover this particular result. So this I was looking at your paper with Victor and Olga and Chitov, and we had it on the table, and we had a fish diagram on the blackboard, and my friend was saying, Xerxes was saying, hey, how do we understand this axiom? We knew that we wanted this axiom. This axiom was in your paper. And I was looking at the diagram and I thought, wait, if I write this long fish, this 5 triangle fish, I can see that I see one fish swimming to the right, one fish swimming to the right, but then there's another fish swimming to the left. Right? So the first pattern matches here, you get the tail, ABC. Second pattern matches here, you get the head, CDE. So these two are the ABCDE, ABCDE here. But then the middle one is swimming in the opposite direction. And because the labeling goes tail, body, head, it has to be reversed. Yeah. So then, we found also this axiom. It was very elegant. So this to me is it's a very powerful narrative, right? You begin with this very simple example of associativity, and then you find identities, then you find daggers, then you find operats, then you find semi-heaps. It seems very powerful. So the idea, so this was the paper. We call it heaps of fish, just to make the joke. So the idea is to really generalize this thing. So we call these things schemoids. I don't want to get too much into the specifics, but the idea of this, and we have it in Mathematica, is that you can computationally now write all possible initial states and see what state will lead you into confluent diagrams like the ones before. And then if you have such a situation, which is not trivial, because, only very special initial states are going to be confluent in this way, because most of them will just have several branches and won't get to a single confluent point. And the question is, okay, if I find such confluent systems, then I'm going to try to label things consistently in my first initial state, and then see what ambiguities I get at the bottom. So, for example, this diagram here, I don't think I have, let me see if I have the notebook where I had this.
So the first step is terminal multiplication. It's there.
Yes. So the first step.
Here. No, down.
Here. Yeah. No, but the steps goes from the top to the bottom. Yeah. So you begin with this. So this is your product actually, and applying your product, each of these triangles, right, is one of these products. Yeah. So if I operate this, I get this. If I operate this, I get this. If I operate this, I get this. Yeah. Right? And then I can still operate some, because there's some pattern there and some pattern there, and so on. The point is that at the end I get only 3, and then those I can operate and I get a final result. So if you look at what that formula is, it's kind of easy to see, but the formula that represents, if you notice, is that I have to write something that is the product of 3, multiplied with something that is the product of 3, multiplied with something that is the product of 3. So that looks like, A, B, C, X, Y, Z, P, W, U. Yeah. And then each of these is a hypermatrix, and you just multiply this together. Mm-hmm. So that formula is this down. Yeah. And so you say, wow, but it is confluent. Why doesn't it give you some interesting axiom? And it's a 9-element, right? If it is. So the problem is that the confluence of this diagram only corresponds to the freedom that you have to order the operation. You can first operate this, then you will get this diagram, or you can first operate this, and you will get this diagram, or you can first operate this, and you will get this diagram. And then you have 2 things remaining, which you can then operate in whichever order you like. So what this diagram is telling you is that no matter the order that you choose to operate your brackets, you're going to get the same result in the end. But it's not telling you that there are 2 ambiguous ways in which you can operate your brackets, which is like the other axis before.
But inside the brackets, do you fix the elements?
Yes. So the elements are all fixed in the beginning. Here, it's just too small, but you would see like A, B, C, X, Y, Z, U, T, U, W, T. Right? So it will all be fixed in the first diagram, and the confluence property of this rewrite system of this directed graph only tells you that there's a freedom in which order you operate your brackets, but it doesn't tell you that it should be associative. So this is just a cautionary example to tell you that confluence is not enough. You need confluence, but with something else. The something else is what I call overlap. which is could be understood as what Nick was saying yesterday about causal dependence.
Yeah.
So when you have the thing that is common to all these patterns before is that
algebra as associativity.
yeah. So what is common to all this is that your initial state had overlapping matching patterns.
Mm-hmm.
So the three fishes. So it is true that there are three fishes in the first pattern, but not only that, they are overlapping. Right. The first fish is sort of overlapping the body and head is overlapping with the head and body of the second one, and so on. Right. And so every single pattern that you see in here, has overlapping patterns. Like, for example, here, the pattern there is overlapping the whole thing. So it's already mixed. When the second rule applies, it's applied to something that is already mapped. Here is one single thing, so it's overlapping to the whole thing. Same thing here, and here the same, right? So in here, my pattern, which is this V shape, just two edges, one matches here, the other matches here. So G is an overlapping of both matches. So my hypothesis for the last couple of years has been, and we're still working on how to make this practical and operable. My hypothesis has been that you can define a property of rewrite systems that are simply defined in terms of pure edge rewriting that have very strong confluent, a stronger condition than just confluent. So they are confluent for sure, but they are also confluent in this special way in which the patterns are overlapping throughout, that will detect what we call associativity. And so my strategy to find the associativity of these products is to write take the product, write the Plex diagram, so write the triangles or whatever, and then try to search for these kinds of rewrite processes. So far, we found none. So far, we haven't done extensive searches, but we know, for example, that if you want to up to 9 elements, right? Up to 9 elements involving 9 axioms involving 9 elements. There are, so you might be wondering, how many initial hypergraphs are there that you can, of this kind? In the last slide, how many hypergraphs of this kind involving 9 triangles are there? So these are simple connected, right? So it's not. There are 12,500,000 such hypergraphs. So there's a lot of them, right? And so the idea is that if there are any properties that, like associativity, that involve at least 9, or I mean at most 9 elements, they are going to be represented by a pair of an initial state with at most 9 triangles and a choice of rewrite rule. The problem is that rewrite rules, we really don't have that many. We have like 3 or 4. We have the Zapata-Carratala, the fish, the 3/4, and so on. But initial states, we have 12 million. Right? And so we could, I mean, this is a manageable size. The 12 million is manageable. Generating these 12 million hypergraphs is not that difficult. But knowing exactly what to search in the rewrite systems that they are generated, that's not so trivial. And that's why we've been sort of like, I've been talking to Nick and to Nicholas Baer, that he presented yesterday, and we are trying to figure out what are good criteria to navigate this very big computational space.
And we don't find anything in the confluency related. I mean, people have been probably using confluency properties in other systems. No?
Yeah, the problem is that our system is like, we need those results for exactly the system. Otherwise, we can't do anything.
It's not enough, but maybe there are. Okay. So
so these techniques are super relevant, but they need to be applied exactly to the system for it to generate any meaningful answer for our question. Because the question is not about this system. The question is it's a related question in purely algebraic terms.
Mm-hmm.
This diagram is just a guide to allow you to discover there. So in order to get any meaningful answer for the algebraic question, you need to apply those techniques exactly to the system. So if, which in my opinion, kind of reduce to the same question, because you will give, Nick will take the rule and he will find the rule algebra out of it. And in the process, he will find all the overlaps. So if he does it correctly, he will probably find what we are looking for. My worry is that the rule algebra that he works with is binary. So it means that you only really need to look at overlaps of the pattern with itself once, or 3 times. So, I mean, 3 times might be enough for this because that seems like the right cardinality. But the point is that
What do you mean once? So do you do like FGH equals FGH with brackets moved, or what do you mean once?
Once meaning the number of nestings that you allow. So applying once means that you only have one bracket.
Yeah.
Applying twice, it means I have one nested into another 3 times and so on.
Not this one.
That is 4 times, right? Because it's 1 big bracket and 3 inside. So the results will. I mean, I think the thing is that my understanding, and if Nick watches this or gets some air from what we're saying here, I think we are just studying a rewrite system primitively, right? We are not using rewriting as a technique in some other study. Like our question is really, this rewrite system, how does it behave? So absolutely, their techniques are going to be relevant because they have, they study abstract rewrite systems, so it's absolutely relevant. But in a sense, they will only be relevant when they are applied literally to this case. In which case, if they produce something like a result that I might want to hear, like there are no such confluence systems in your 12,500,000 set of hypergraphs, then that's an interesting result, because then it really is a full confirmation that you should not expect axioms of this kind. But anyway, that's kind of the point of the talk. Many of you already know this, but all my findings and my collaborations are on this page, ret.science. You can find my papers there. But that's all I wanted to say. Thank you very much. So,
until I forget.
Yes.
There's something that I remember now, that Jacobi identity for ordinary Lie group
Algebra.
is derived from associativity of the Lie group.
Yes.
I don't remember exactly if it's in Tupikina's book, and you just define the Lie group and the dimensional group with n coordinates, and then the new element is given by n functions of n coordinates.
Yes.
So these n functions of n coordinates, suppose that now you make another product, we get iteration, then you require that associativity. And somehow, when you differentiate it, at the end,
you get Jacobi.
You get the Jacobi.
Yes.
So now, if maybe we could approach the associativity in algebra, but no, sorry. The algebra is not associated.
No.
But the Jacobi identity comes
from associativity. Yes.
So maybe the general Jacobi identity will come from associativity in any group.
Exactly.
But how to define
n-area associativity?
Group,
yes. Exactly. That was my question, yes.
Yeah, what is in usual groups, the central thing is the unit element.
Sure.
Once you have unit element, you have inverse, and so in n-areas, so you have to, either you have 2 unit elements that come together and they reproduce, but then is it possible to have a unique inverse?
So
you have 2 inverses.
Yes.
Because you have first and second unit. I don't know, but I think it just depends on the ternary group.
So
Group.
Yes, group. Yes. Groups. So there is literature on what have been called this I think some Polish authors on can't remember the name is escaping right now, but there is a fair amount of literature on what having called p-adic groups or n-ary groups. But a simple check that you can do is if you take a p-adic group in this sense and you try to compute the infinitesimal component, or if you take a p-adic associative algebra and you try to define the commutator or something like that, you will find that you don't get.
P-adic is some p-adic numbers.
No. So p-adic is the historical name. It means n-ary. N-ary, yeah. It's n-ary. The n-ary groups. Dudek is the name. Yeah. Dudek. Yes. Dudek is the name. Yes. So they do n-ary groups, which assume n-ary associativity, and n-ary associativity really means that you have an n bracket and you can move it in any sequential direction. But they also do weak n-ary groups, meaning that you don't assume some of the associations of the bracket, and then you assume some permutations and whatnot. So in all that literature, there's no construction that taken that and made infinitesimal, or taken that as an algebra and made a commutator out of it, gives you a Jacobi, a generalized Jacobi. It just doesn't work.
Yeah.
So it's a valid theory. There's nothing wrong with it. In fact, there are some results that are interesting.
Going to infinitesimal should give you something.
It should give you something, I agree, but it's not.
It's not a Jacobi.
It's not a Jacobi identity. Yeah, it's interesting. Yeah, but yeah, going to infinitesimal is interesting. So actually, what I mentioned on Monday about the bi-units in semi-heaps, that could be an interesting. I didn't follow up, but it could be an interesting exercise.
Yeah, so I think I understand why it's difficult to go to infinitesimals, because going to infinitesimals in the usual group means that you have the unit element.
Yes.
And from this unit element, you just go. I needed 2 unit elements. Really?
Well, that's one way to see it. Another way to see it is to think about invariant vector fields.
Yeah.
So one way to see the algebra is that it's the tangent space at the identity. That's one perspective. Another perspective is that it is a finite dimensional Lie-sat algebra of the Lie algebra of vector fields generated by the left invariant vector fields. Right, and the left invariant vector fields are simply the vector fields that are equivariant with respect to the left action of the group on itself.
Yeah.
Right. So if you have an analog of an action in your object, you can define the whatever invariant vector fields or whatever invariant bivector fields. So my guess is that the analog of the infinitesimal analog of these kinds of things in the ternary smooth manifold with a ternary operation. I'm not assuming it's a group. It's just smooth manifold with a ternary smooth operation.
Yeah.
I'm not assuming any associativity. The analog of an infinitesimal vector field would be an infinitesimal bivector field, because you would have, you fix one entry for the action, and then you have 2 entries left. So in the binary case, you have only 1 entry left, which is where you put your 1 parameter group. Here you have 2 parameters. So 2 parameters span a surface. So that's a bivector infinitesimally.
Okay.
So in fact, I actually had a formula that was similar to the formula. This paper, Chinese paper, where they find the Jacobi identity with a combination of traces and products? There's a paper. I should find it. It's not very interesting in my opinion, because it basically just concoct this product where I think it looks something like this. It looks like you have A, B, C, and you trace of A times bracket of BC plus, and then cycling, right?
Yeah.
Trace B, A. Right?
Yeah.
So it looks something like this. I think that satisfies Jacobi identity. But I never made anything of it because it is binary. So it's made of matrices. So it doesn't really give me anything ternary. It basically built this Jacobi, ternary Jacobi.
It's kind of it gets you completely out because
yes.
See the bracket. This is ordinary bracket.
This is ordinary matrices and ordinary brackets.
So the bracket bracket is always traces.
Yes.
So usually, for example, the algebras, most of the time, when they're represented by matrices, these matrices are traces. But if you work on traces matrices, you can 0, 0, 0.
Yeah, but so the claim is
These matrices are traces.
Yeah. But no, but these matrices are generic. The claim is that the claim is
how the matrices are generic, but then you project go into traces.
Sure.
So if you iterate it, what do you get?
You mean that it has no physical meaning for you?
What, traces?
No, what they form. I mean, what they define.
No, I'm looking at algebraic.
Yeah.
If these are whatever matrices, if these are matrices,
So the derived algebra is already 0.
Yes. Are also matrices, but they are traces by definition. Because the trace of a product does not depend on the order. So the trace of BC is the same as the trace of CB. So the trace of the CB is 0. But here you have not yet took the trace. You didn't take the trace, you take only the trace of this generic matrix. Okay, first it works. But now this result is the trace of matrix. So if you continue, you cannot continue with it.
Yeah.
It's over. The game over. Because if you try to apply the same formula next time to the result, it gives you nothing. There's kind of the important thing. No extension. You take first any matrices, you formulate this is very good, but how you get Jacobian, I cannot understand. Because in order to get Jacobian, you have to iterate again, right?
I'm trying to find a paper where they define this bracket. No, I don't think it was this one. I remember it was. Here we go. I think it's this one.
So, can I say, do you hear me?
Oh, yes, Victor.
I remember that you mean the ternary algebra where the ternary commutator was constructed by trace and commutator of two matrices.
Yes.
This was a paper physicist published. I don't remember the names.
I think I found it. I think I have it on the screen. I think they define at some point down here. I think they define this bracket, but no, wait, it should be in the beginning.